Okay, this discussion is about a typical commercial refrigeration low temperature box. This is the electrical diagram typical to what you would see in a self-contained or possibly even a walk-in refrigeration system. This diagram that we are looking at is pretty much typical to those kinds of systems. So starting at the beginning of the diagram, we see that we have a switch that controls only one leg of power. That's our master system switch. So by that we could assume that this is a 120 volt self-contained reach-in type low temperature refrigeration box. At the top of the diagram, the first things we see are the mullions heaters. And the mullion heaters are wire type electric resistance heaters that are used to keep the door jambs of all refrigerators and freezers above the dew point temperature of the air so that the doors do not sweat or freeze. Below that we see the lighting circuit typical to just like your typical domestic refrigerator you might have in your home. We have the lighting circuit connected to a door switch. When the door opens, the lighting circuit is energized. We have lights come on, interior lights inside the box come on, and when the door switch is closed, the lights go out. Below that, within the dotted black lines here, is our defrost timer, our defrost clock. Outside of the larger dotted box is our electric defrost heater connected to a high limit switch. The electric defrost heater is in direct physical contact with the evaporator to melt the frost off of the evaporator so that we have the correct airflow. The evaporator doesn't get blocked with frost and ice. The limit switch there is to protect the whole unit from going above a predetermined temperature that could be damaging to the unit. So we have a high limit switch here in series with the electric resistance heater. And normally we'd also see as a safety fusible links, but this diagram is very generalized. Anyway, within the within the black dotted box is our defrost clock. It consists of a shaded pole timer motor and a set of normally open and normally closed contacts. The normally open switch between 2 and 3 is always going to be connected to our defrost components. In this case we're using electric resistance heat, but a hot gas solenoid valve could be here in its place if we were using hot gas defrost. Between 2 and 4 is the normally closed switch, and the normally closed switch is always connected to our refrigeration components. Down below we see the first item connected to the normally closed switch is our evaporator fan motor. In commercial refrigeration system, the evaporator fan motors operate continuously except during the defrost cycle. Otherwise, the evaporator fans are on 24/7. Below that we have our thermostatic switch, which will cycle our refrigeration system down below here on and off with the the desired temperature range. Then we have optional high and low pressure safety switches to protect the refrigeration system from a low pressure or high pressure event on the high or low side of the system. Looking at the refrigeration system itself, the first thing we see in the first rung here of this ladder diagram is our condenser fan motor. They have a simple shaded pole motor being shown here for a condenser fan motor, so this again suggests that this is a small self-contained reach-in freezer. So as you see, connected in series with the condenser fan motor, we have a pressure switch. This is a condenser fan cycling switch to be able to control the condenser fan motor for low ambient control. So if this unit is placed where the condenser is subjected to a low ambient, low temperature below 65 degrees, this pressure switch would cycle our condenser fan motor on and off to maintain a minimum high side pressure. Below that we see our compressor motor. It's a CSCR motor circuit here. It's a capacitor start, capacitor run motor circuit, so that would suggest to us we're using a TXV metering device. Here is our run capacitor between run and start on the motor windings themselves, and below we have a potential relay that is controlling the start capacitor located here. And the potential relay, that's all it's controlling is our start capacitor, which is there. I'm sorry. That's our normally closed switch on the potential relay. Here's our start capacitor here, in parallel with the run capacitor. So that's our refrigeration system. This is the only part that's going to cycle on and off with the thermostatic control. Okay, so the most complex part of any commercial refrigeration system is the defrost circuit. So I want to focus on the defrost clock and its operation. So between points 1 and N on this particular kind of clock is the timer motor. Again, that's a small shaded pole motor. Very little can go wrong with it, but it can burn out. Sometimes they do burn out and the clock will no longer advance. We'll talk about that. So we have, again, the normally open contacts are always controlling our defrost component, and the normally closed contacts are always controlling the refrigeration system. You can actually commit that to memory. Normally open, defrost. Normally closed, refrigeration cycle. Between 3 and X, coming off the normally open contact, we have what's called a defrost termination solenoid, or otherwise known as a finishing solenoid. Between 3 and X on the defrost clock, point X, is the finishing solenoid. And what that does is it allows the defrost to be terminated by temperature. And the most common component used for this kind of control is the defrost termination fan delay switch, which is a single pole, double throw thermostatic switch. It is also located on the evaporator, sensing the actual physical temperature of the evaporator. The thermostat has a cold point, if you will, and we'll know that as point 1 as labeled here on the schematic, and the hot point, which is labeled by point 3 on the schematic, and point 2 on the switch is where line power is fed in to complete the circuit. So under normal operation, when the evaporator is cold and we're in the refrigeration cycle, the defrost termination fan delay switch is keeping the evaporator fan energized. When there is a call for defrost, the normally closed contacts between 2 and 4 will open up, which will turn off the evaporator fan, and our refrigeration system below, our compressor and condenser fan, will be cycled off, and contacts, the normally open contacts between 2 and 3 will close and bring on our defrost component. Now the evaporator begins to warm up. Once all the frost and ice is melted off, the defrost termination fan delay switch can terminate the defrost cycle by temperature. Defrost could be terminated either by time or temperature. That's what the defrost termination fan delay switch and the finishing solenoid on the clock do for us. It gives us that ability to be able to terminate the defrost on a temperature. So when the defrost termination fan delay switch makes to its hot point, it will energize the finishing solenoid and allow these contacts to flip-flop back to their normal positions. When the finishing solenoid is energized, points 2 and 3, the normally open switch, which was closed for the defrost, will open up turning off our defrost component, and also de-energizing the defrost or the finishing solenoid. The normally closed contacts will close again and turn on the refrigeration cycle again. It will start the compressor and the condenser fan motor, but the evaporator fan motor is delayed on. It's delayed on by the defrost termination fan delay switch. This component literally lives up to its name. It terminated the defrost on temperature, and it's going to delay the evaporator fan from coming back on until the evaporator has come down well below 0 degrees Fahrenheit. Typically, the hot point to terminate is 45 degrees Fahrenheit, and our cold point is somewhere around 0 degrees or below 0 degrees Fahrenheit. Some of these are fixed and some of these are adjustable. There's different types, but they all function the same way. So once we get to 0 degrees or below, we'll make to our cold point, and the evaporator fan will then be turned on. The reason for doing that is to avoid rejecting heat that was created by the defrost cycle into the conditioned space of the box. So I'd like to demonstrate the defrost clock itself physically. On a commercial refrigeration system, it'll be located in a box like this. Sorry, I was holding it upside down. This is a typical Paragon defrost clock. There's many brand names, but Paragon is very widely used. And it'll be in an enclosure just like this. To open the enclosure, you just simply pull back on this tab, and the door just simply swings open. For easy, if you need to do troubleshooting for ease of, or for convenience anyway, the door is removable. You just lift up on it and you can get it out of your way so that you can easily work on it. The way the defrost clock works is, it is a 24-hour clock. The section here in the black zone here, black highlighted numbers here are PM hours from 6 p.m. to 6 a.m. And our lighter side here of the clock is our PM, or I have it backwards. The lighter side is PM and the dark side is our AM hours. So these are our hours. The time indicated is where this arrow points, and it says time right here. So right now it's pointing at 10 p.m. In the evening. The center dial is the duration adjustment. This is where we can set the duration of the defrost cycle. Right now the indicator is set for just a little bit less than 10 minutes, so it's set for 9 minutes. Typical for this vicinity of the country, here in the Central Valley of California, 15 minutes is adequate. To adjust this duration time, you simply push in on this copper pointer tab. You push down on it and push it to one side to make your adjustment. And I need to get it right in between 10 and 20 minutes to indicate 15 minutes. So with that setting, the defrost clock will terminate the defrost after 15 minutes if the defrost termination fan delay switch does not terminate it by temperature. So the things that can go wrong with a defrost clock is the timer motor can fail. It can fail either in the freeze cycle or sometimes a couple times in the field I have seen where the defrost clock failed during the defrost cycle, so it was literally stuck in a defrost. To be able to better see the workings of the defrost clock, and also to better be able to troubleshoot it, the clock is easily removed from the enclosure by pushing outward on the same tab that we used to open the door. If I push it outward, I've just released it, and I can pull the whole mechanism out of the enclosure. And now we can better see the clock both sides. So we see the clock here, and as I've described here, here's our time settings. And to set the time, you just simply turn the dial so that it moves clockwise. It will not go backwards. You can only go one direction, so if you need to get back to 10 p.m., which is where we started, you would need to advance the clock all the way around. Wherever you see a pin, that's where the defrost is going to begin. In this case, the pin is at 8 a.m. or 8 p.m. I'm sorry, that's 8 p.m. there. And I'm coming around to 8 p.m. And when I get there, and as it starts to pass by the time indicator, it will cause you'll hear a clicking sound, cause the clock to go into the defrost cycle. What you just heard were the switches flip-flopping. The normally open was closing and the normally closed context opened. So then the time goes by and then it terminates it after 15 minutes. So now I want to demonstrate to you what's going on the back side of the clock. On the back side of the clock we have our timer motor and the finishing solenoid that we were discussing. When this solenoid is energized, it pulls this plunger up, magnetically pulls this plunger in, which, if you can get a side view of it there, pulls up on this lever that's attached to it that allows the clock to go back to its default positions. So I'd like to demonstrate that for you. And here's our contacts.